All right, let's jump right into this explainer. Today, we're unpacking something called Copy.fail. We're going to look at a surreal, honestly devastating vulnerability that completely redefines how we need to assess enterprise Linux security. Seriously, if you're an IT risk assessor or a cybersecurity pro defending a modern network, this is an exploit that you absolutely need to understand.
You know, security researchers are actually calling this one of the most beautiful exploits, and honestly, there's a really good reason for that. It is a universal root exploit. What makes Copy.fail so incredibly dangerous to enterprise environments is that it completely bypasses traditional version-specific patching. It doesn't rely on some narrow race window, and it doesn't need a kernel-specific offset that changes from one Linux distro to the next. If an attacker gets even a tiny foothold on a machine running almost any version of Linux since 2017, well, this bug basically hands them the keys to the kingdom.
So here's our roadmap for today. We'll hit the universal Linux threat, anatomy of the socket, splicing reality together, enterprise business risk, and finally, mitigating the exploit.
Okay, Part 1. The Universal Linux Threat, a real patch-resistant nightmare. What makes this threat a genuine nightmare is that it's not your standard flaw. It's a deeply embedded logic bug. See, traditional vulnerabilities usually break from one OS version to the next, which gives defenders at least a little bit of breathing room. Logic bugs, they just don't care about your specific distribution. The fundamental logic of the operating system itself is what's broken here, and that brings us to this staggering number, 732. A mere 732-byte Python script is literally all it takes to achieve local privilege escalation across these systems. No complex compiling, no hunting for memory offsets, it's incredibly pervasive. An attacker with standard user access can run this tiny, whisper-quiet script and elevate their permissions to root, totally bypassing traditional endpoint defenses that are busy looking for bulky, noisy exploit kits.
Moving on to Part 2, Anatomy of the Socket and the Cryptographic Landscape.
To really understand how this embeds into the kernel's memory management, I want you to imagine the inside of the Linux kernel is this strange, floating, almost DALI-esque landscape of data structures and memory pages. Right at the heart of this landscape is the AF_ALG socket. In Linux, everything is a file, right? And its socket is basically just a type of file used for communication. The AF_ALG socket is a specific subsystem that lets regular users run cryptographic algorithms using the kernel's built-in systems in hardware accelerators. And the thing is, we actually want developers to use this. The golden rule of cryptography is never roll your own crypto, so relying on the kernel's optimized hardware-accelerated socket is absolutely the right way to do things.
But a socket needs to know where your data is. Enter the scatter lists. Think of these as linked chains of memory pages just floating across the CPU. If you send a massive chunk of data, it naturally scatters across varying pages in physical memory. The input scatter list tells the kernel exactly which pages to read from, and the output scatter list tells it where to allocate new pages to write the resulting encrypted or decrypted data.
So the crucial point here is the strict sequence the kernel expects when using these sockets for something called authenticated encryption with associated data, or AAD for short. The kernel's contract expects data in this exact order. First, the authenticated associated data, second, the ciphertext, which is the actual encrypted stuff, and third, the tags, which act kind of like a signature to prove who the data is from. When you send a message, the kernel faithfully lines up these pages in the input scatter list, perfectly ready to process them.
All right, Part 3, Splicing Reality Together. Time to bend the kernel.
We are now entering the surreal core of the exploit mechanism, where reality inside the kernel just starts to melt and splice together, turning a secure crypto function into a massive enterprise security nightmare. It all traces back to a fatal flaw introduced as a simple optimization way back in 2017. In theory, the input scatter list is strictly read-only. But for the sake of optimization, the kernel was designed to use a reference to the input tags page as a temporary output scratchpad for certain IPsec crypto algorithms. Let that sink in. This means a supposedly read-only input page is dangerously overlapping with a writable output function.
And here is the mind-bending logic of the attack. Instead of sending all three expected pieces of data, the attacker sends just the AAD and the ciphertext. Then, they open a highly privileged program, specifically the SU binary, which, as we know, is used to switch users. Doing this creates a cached page of the SU program in memory. Then comes the magic trick. The attacker uses a Linux function called splice to literally pipe the file descriptor of the SU program right into the crypto socket where the tags were supposed to go. So the kernel thinks it's looking at cryptographic tags, but it's actually looking at the local page cache of a highly trusted system binary.
Because of that 2017 optimization we just talked about, the IPsec algorithm now uses that spliced page as a temporary scratch pad. The algorithm writes sequence numbers, basically 4 bytes of scratch data that the attacker completely controls, directly into the cached memory of the SU program. And because the splice function allows the attacker to specify an offset, they can write 4 bytes at offset 0, then 4 bytes at offset 4, and so on. They are literally overwriting the cached SU program byte by byte with malicious shellcode. When the attacker then executes SU, the kernel runs their shellcode as root because it still sees SU as a trusted, privileged binary. It's wild.
Part 4. Enterprise Business Risk. The 48-minute countdown.
Let's pull back from the surreal kernel memory for a second and anchor this directly to the hard reality of enterprise risk management. Why does a local privilege escalation bug matter so much to a CISO? Well, this number is exactly why: 48 minutes. On average, once an attacker achieves local privilege escalation, meaning they've upgraded their basic access to root access, it takes just 48 minutes for them to compromise an entire organization's network. In today's threat landscape, an attacker might just phish a low-level employee or buy a cheap compromised credential on the dark web. That gets them in the door as a basic user.
Copy.fail is the master key that turns that minor breach into a total network compromise. The business risks here are severe. It applies universally across distributions. It doesn't require any noisy, complex tuning that your endpoint detection might catch. It provides silent, immediate root access. From a risk assessment perspective, this vulnerability essentially guarantees that any minor intrusion on a Linux server is going to result in rapid lateral network movement and full system takeover.
And finally, Part 5. Mitigating the exploit. Closing the socket.
So what do we actually do about this? Let's move to the actionable steps IT risk assessors and sysadmins need to take immediately to secure their environments. We have to close this socket. The absolute primary mitigation is right here. You need to ensure your systems are patched to include mainline kernel commit A664B. This critical commit fundamentally reverts that flawed 2017 in-place optimization. It ensures that the input and output scatter lists are securely separated once and for all, preventing the kernel from ever using an input page as a writable scratchpad again.
But we all know enterprise patching takes time, right? Sometimes you have legacy systems that just can't be immediately rebooted or updated. If you cannot apply commit A664B right away, you need to look at the AESAD crypto module. If it's compiled as a separate loadable kernel module on your systems, you can administratively remove the module and configure your systems to prevent it from loading on boot. This temporarily neuters the vulnerability while you get your deployment of the kernel patch ready. I want to leave you with a final thought to take back to your security teams today. Are you relying purely on version-specific patching to protect against logic bugs? Because Copy.fail proves that the most devastating exploits aren't always the noisy, complex memory corruptions that break from patch to patch. Sometimes they are elegant, universal flaws in the core logic of the system itself. Reevaluating how your enterprise detects and mitigates these patch-resistant logic bugs isn't just an IT task anymore, it is a critical business imperative.